So we were talking about the different path lines, okay? And we said that at t equals 0, we obtain that the path line of the particle passing by the origin at t equals 0 will give us the vertical line x equals 0, okay? Now, when t was equal to pi over 2 omega, we demonstrated that the path line is a straight line of slope v0 over u0. Now we can show that if we draw all path lines for different times, we'll cover a cone limited by a line of slope v0 over u0 and another line of slope minus v0 over u0. How to explain this? To explain this behavior, let us go back to the expression of dx by dt and dy by dt. So if you remember, when we wanted to find the equation of the path line, what was the strategy? So we said that first we have that by definition dx by dt is equal to the component of velocity along x, which is u component, which is a sinusoidal function of t. And we have that dy by dt is v0. So here we might say, but this is a sinusoidal function of time. How at the end we got a straight line for the path? To understand this, as I told you before, when you want to integrate here with respect to time, you should make sure to replace y by its function of time, okay? And we said that y is a linear function of time, and we found its expression from the streamline, from integrating y with respect to t, because dy by dt is equal to a constant v0, so y is v0 t plus c1. And then we said we cannot integrate this relation with respect to time before replacing y by its value. And y is linear function of time. And when we replaced y by its value, what happened is that t canceled out, because here if you develop, you have v0t minus v0t plus c1 over v0. So v0t will cancel out and you end up only with dx by dt is minus u0 sine c1 omega over v0. So the time here canceled out. And this means this is explaining why path lines will be straight lines, because x is not sinusoidal function of time. X is linear with respect to time because c1 is a constant. And the slope of variation, if you want, of x with respect to t, will be or positive or negative depending on the constant c1. This is why we will have a region where, for which when we draw the line will have a positive slope, and other regions where the slope will be negative. Because y is, as you can see, for all path lines, y will always increase because dy by dt is positive, is equal to v0. While the x by dt can change in sign depending on the value of constant c1. Okay, so now how c1 can vary? C1 can vary depending on the time you consider. So here we are interested at for path lines passing by the origin at different times. Now, why we will have a repetitive behavior here? Because if we go back to our relation, okay, you have this sinusoidal aspect by when defining u. So you have that from this given u is equal to u0 sine omega t. So you have a certain periodic variation of u. And this period, okay, is equal to what? The period t of variation is equal to 2 pi over omega. Okay, this means that if I consider all times t between 0 and 2 pi omega, I can cover all path lines because this will be repetitive since sine this function, sinusoidal function, is a periodic function. So if I draw path lines between 0 and 2 pi over omega, then these path lines will be repeated for new intervals. So what we did until now, we have considered at t equals 0, what is the path line? At t equal pi over 2. If we try together, if we do some analysis together, going to this figure, you have between 0 and pi over 2 omega, you have a positive slope for x, because this depends on the sign of, as we said, the sign of dx by dt. Okay, so you can check that dx by dt will be positive in this interval. And if you continue now, if you increase time from pi over 2 omega until pi over omega, then you will get back to this line. Okay, you can verify this simply by doing what? By finding what is the equation of the path line, okay, for t equal to pi over omega. You will get again that the corresponding equation will be the vertical line. And if you check what will happen for t equal to 3 pi over 2 omega, so I will give you the result, try to do it. For t equal 3 pi over 2 omega, you will get that constant C1 is minus 3 pi V0 over 2 omega. You will have that constant C2 is 3 pi U0 over 2 omega. And when you replace these constants in the expression of x and y, you will have that x is minus u0t plus 3 pi u0 over 2 omega. And you will obtain that y is equal to v0t plus minus 3 pi v0 over 2 omega. So now, if you try to divide y by x, okay, if you try to do, in this case, y over x, you will get minus v0 over u0. This will give you the second limit for path lines. This is the second limit. So as you can see, your path lines will form like a cone. Okay. So you have this region of positive slopes, this region's negative slopes. Okay. And now, if you go for t from 3 pi over 2 omega to pi over omega, okay, then now to 2 pi over omega, then you will close your period. So when you go back to 2 pi over omega, you will end up again here. And now it will be repetitive. So back and forth, I will do this, then this, then this, okay, with time. So now you can deduce how can be your streak line, okay? And for example, if you ejected several particles at the origin, so at different times, let's say you ejected this particle at t equals 0, so this particle will follow the path line of t equals 0. And let's say you are interested to know the streak line at a certain time, so you will say it will become at t equal, for example, anytime, let's say t1. I'm interested to take a photo at t1. If I follow this particle, if I replace t by t1 in the path line of the first particle, I'll get this position. For the second particle, let's say ejected, it will be on another pass line. It will be on the pass line at t equal, let's say, to 1 second, for example. Okay, so I can consider different times, and if I each particle will be on a certain pass line, okay, corresponding to the time of generation from the origin. And the last particle I generate at the origin will be here. I will see it here. So now, if you draw your streak line, you will see this. Here you will see like a oscillating profile, because you will go from one pass line to the other. So as you can see, you can start, you have this particle will be here, the other particle will be there, and this is the streak line showing how particles are moving on different path lines, and I will obtain an oscillating behavior because, as we said, the different path lines will have the formation, will form like a cone. Okay, so you have, let's say, for time between 0 and pi over 2 omega, if these particles are generated between 0 and pi over 2 omega, you will track them here along these lines. Okay, then between pi over 2 omega and pi over omega, you will see this line, and then between pi over omega and 3 pi over 2 omega, okay, you will see this. And finally, from 3 pi over 2 omega to 2 pi over omega, you will see this. Okay, and this is repetitive. So here you can have several, a period of time larger than. So this corresponds, if you want, to a complete period, this path. Okay, and the other particles will start in a new period, in a new cycle. Okay, so this is about streamlines, path lines, and streak lines. Now we move to a description of fluid flows. Okay, so we have already seen before that we can characterize flows by different categories. We can consider the difference between laminar and turbulent flows. So as we mentioned already before, in case of laminar flow, the fluid will move along smooth path. So if I observe, let's say, streamlines, they will be very smooth. Okay, they will be organized and ordered. So no random motion. Okay. And in this case, the viscosity damps any tendency to swirl or mix. So viscous effect will be dominant. They will prevent any mixing or happening in the flow. Okay. While and how I can characterize laminar and turbulent from Reynolds. So for each type of fluid, you have a range of Reynolds which correspond. For small Reynolds number, it's laminar. For larger Reynolds number, it's turbulent. And each type of flow is characterized by a certain limiting Reynolds. So if you have flow over a flat plate, it's different than, let's say, flow over a cylinder. So for each type of geometries, I will tell you, below this number, you can consider, below this Reynolds number, you can consider the flow laminar. And above this Reynolds number, you can consider it turbulent. Okay, and you have a small, if you want, transition zone. So you have some Reynolds numbers in between where you have a transition from laminar to turbulent. Now, turbulent flow is characterized by what? It's characterized by very irregular paths. So you have, let's say, very random motion, and this is, if you want, you have mixing effects. Yeah, as you can see here. Okay, so this is an example of turbulent flow. You see a lot of turbulence, a lot of mixing, a lot of swirl in the flow. While here, for this jet of water, it's very smooth. Okay, so this is laminar, this is turbulent. In case of turbulent flow, we have efficient mixing, and we have velocity. At any point, the velocity will fluctuate. So we have, if you want to observe the velocity variation, it will always fluctuate around a certain average value. Okay, if you have, this is in case of steady. So even if the flow is steady, in this case, you still have, you cannot characterize, to say steady, you should just define an average velocity. So it can be, even if it's turbulent, it can be steady, but when we talk about steady flow in this case, we mean that the average is not varying. But always when you observe the velocity profile, it will always oscillate around this average. Okay, so this is why we say the velocity at a certain point will always fluctuate with time. Okay, but when we say it's steady, then V average is constant. The average is not changing, but I still can observe fluctuation around this average. Okay. Now, another categorization of flow is the temporal spatial classifications, which we mentioned already before. So we can divide into steady and unsteady flows. So this means whenever we talk about steady, unsteady, we are characterizing flow with respect to time. So if it's changing or not with respect to time. To say steady, this means that if I observe velocity at any point in my domain, the velocity is not changing at this point. It can change from point to point. This is non-uniform, okay? But this doesn't mean that it's unsteady. To say it's unsteady, if I observe at the same location the velocity, it should vary. If for any location the velocity will remain the same at this location, then it's a steady flow. Okay. So example of steady flow, you can consider whenever, let's say, you have any dot, you have constant mass flow rate, m dot is constant. Okay. So this will lead to a steady flow because at any location, what's coming in will get out. And therefore, at any location, you can find the velocity from saying that V is equal to rho, is equal to m dot over rho times area. Okay, because m dot is defined as rho times A times V. So it's true here in this example that velocity can change with location if the cross section is variable, but at the same location, it's not changing. And this is what is interesting for me. If I consider one specific location, the velocity is not changing. So this is steady, okay? But it can change from position to position, of course. So the average velocity first will change as we move in this direction because the cross-sectional area is increasing. So V average will decrease. And even if, in case we consider laminar flow, even if I consider a constant cross-section, I have, it's a non-uniform flow because the velocity will change with space. Since near walls, the velocity is 0 because of viscous effect, and it's maximum at the center line. So this is, if m dot is constant, then I have at any point, the velocity is staying the same, but the velocity is varying with space. So this is non-uniform flow. Okay. So now, when we talk, this is, we already tackled uniform and non-uniform. So then we look at changing in space. So whenever we have change in space, change with velocity, when we change in space, we say the flow is non-uniform. And if the velocity is the same everywhere in the domain, then it's a uniform. Okay. Now we move to the section of material derivative. Okay, so whenever we consider a fluid domain, if you remember, we talked that when we consider a fluid domain, we can define velocity with respect to position and time. So we can consider that with respect to the domain, the position variable and time are independent. Here, why they considered, they put xa function of t, ya function of t, za function of t, because a is considered as a particle. So whenever x coordinate is referred to the particle, as I follow the particle, of course, x of it will vary with time. So because they mentioned x at a, so we are considering here the position of a particle, then we can put xa function of time, ya function of time, za function of time. But now, when we want to express the acceleration in of particle in a domain, okay, then in this domain, we can consider that x, y, z, and t are 4 independent variables, and therefore, when we want to do the derivative, the total derivative of velocity with respect to time will be divided into partial derivatives, because you know that when we have a function that is multivariable, then when we do the dv, when we want to write dv, the total variation of v will be equal to del v by, you derive first with respect to the first variable, let's say here time, let's consider t as the first variable. So del v by del t times dt. Okay, let me erase and write. So we can write that dv is del v by del t dt plus del v by del x dx plus del v by del y dy plus del v by del z dz. Okay, so when I consider a flow domain, I can characterize with respect to these 4 variables. And now, since I am interested in dv by dt, if I divide by dt, what will happen? So this dt will cancel out. I have here dx over dt, dy over dt, and dz over dt. And I can say now that when I talk about the x with respect to dt, then I am considering a particle and I follow it with time. And this is the Lagrangian approach. So if you want, this relation here will relate Eulerian approach to Lagrangian one. Because when I want to observe a domain, a certain fluid domain, I observe a certain location. And I want to derive the property at this location with respect to time. I should consider variation with time and variation with position. And to consider variation with position, it's like I'm tracking a particle. And by definition, dx by dt is the component of velocity u of the flow. Dy by dt is v, and dz by dt is w. So in this way, I found out that in a fluid domain, to find the total derivative of a certain variable, I should consider its local variation with time. This term represents the local variation with time. Why I am saying local? Because this will take into consideration variation of velocity with time at the same position. So without changing position, if I look at the same position and I observe variation of velocity at this location, then I will have del v by del t. So in this case, the flow will be unsteady. However, if I observe this location and I still obtain always same velocity with respect to time, this means that my flow is steady, and then this term the local acceleration will cancel out. Now, the derivative of v is not restricted, the total derivative of v with respect to time is not restricted to the change of velocity at this point with respect to time, but also is related to how this velocity is varying with space. And this term, the summation of these 3 terms, will illustrate if the velocity is varying with space or not. So if I have variation of velocity in space in any direction, x or y or z, then I will have acceleration with space. I can have acceleration in all directions also, okay? So this is why we say that the total derivative of a variable in a fluid domain can be divided into the variation, the local variation with respect to time, and the variation of the variable with respect to space, okay? And we can apply material derivative for any variable, not only velocity, It can be applied to pressure, to temperature, to any variable that is characterizing my flow. Okay? So now, since we developed here a vectorial relation, this is a vectorial relation. So all of these, as you can, whenever you see bold letter, this is a vector. Okay? So here you have vectors for VA everywhere. So all you have to do then, okay, is that you can decompose this relation into three relations: one in X, one in Y, one in Z. Okay? So here, this is what we did here. We just replaced the vector by components. So we obtain, this is the result along X. All you have to do then, what is the component of vector A? It's AX here. What is the component of vector V? It's U. So I replace here vector V by U. I obtain del U by dt. This is already U. Here it's a vector V. I replace by its X component, which is U. So it's U del U by del X plus V. This is a vector, so I replace by its X component del U by del Y. This is a vector, so I replace by its component, which is U along X. So this will give me the acceleration along X. I can do the same to get acceleration along Y. The only difference, as you can see here, will be instead of U here, please pay attention. This U will remain as it is because already in the vectorial relation, it was not a vector, it was U. The vector is here. You have V here, 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 and here. So in AY, you get del V by del T plus U del V by del X plus V del V by del Y plus W del V by del Z. And the same to get the expression of AZ. And in this way, you can calculate your acceleration in the different directions. Okay? And we can summarize this by writing it as if you want, in a mathematical operator, because we have demonstrated that the total derivative is the partial derivative with respect to time plus U del by del X plus V del of the variable by del Y plus W del of the variable component by del Z. And this can be written as a mathematical operator. You can summarize this mathematical formulation by the following formulation, which is d by dt of a certain variable equal to del by del t and this variable can be a vector or can be a certain, if you want, any property, and it can be a pressure, which is not a vector. Okay, so you can obtain, so plus v dot, this is called the gradient operator. So it's v dot product, the gradient operator. Okay, but you can just know it in this form, but just for your information, that it can be written also in the following mathematical form. Okay.